Okay, so today's video is part 2 of yesterday's lesson. We are continuing to analyze the different types of matter in order to explain the differences between them. So yesterday we defined elements, mixtures, and compounds, and we also started to compare and analyze the particle diagrams for each types of matter. Okay, so at this point we are able to classify matter as either an element, a mixture, or a compound. Now, within the mixtures, there are two different types of mixtures. So today we're going to practice classifying the two different types of mixtures as either a heterogeneous mixture or something called a homogeneous mixture. So just to review, a mixture are two or more substances that are physically combined in the same container. So remember, a mixture is two or more substances physically combined in the same container. They can be broken down by physical means. And there are two types of mixtures, something called a homogeneous mixture and a heterogeneous mixture. Now, yesterday we discussed some examples of mixtures. So, for example, a fruit salad, salt water, okay? Salt water is a mixture of two different compounds, salt, which is NaCl, and water, which is H2O, okay? Now today what we're going to do is we're going to be seeing where these examples fall under in terms of what types of mixtures they are, okay? So are these a heterogeneous mixture or are these a homogeneous mixture? So a homogeneous mixture is a mixture where two or more substances are uniformly mixed together, okay? Uniformly mixed together means that they have like a constant composition. They're blended, they're smooth, there's no chunks in them. You can't see the individual pieces of the mixture. It just appears to be like one thing, but it is a mixture, okay? Now, first of all, if we use context clues with our prefix, the prefix homo means the same, okay? So a homogeneous mixture is a mixture where it's two or more substances mixed together and they appear to be the same throughout, okay, or blended together. These, because it's a mixture, it can still be broken down by physical means, okay? And one common example is salt water, okay? So salt water, when we have salt water, let's say you took a glass of water, and I'm probably going to show you this in class, and you add salt to it, okay? That salt dissolves, right? Now, when that salt dissolves, those salt compounds, which is NaCl, they're still there. It's just that now the salt has dissolved and it's like part of the liquid. Okay, so if you look at a glass of salt water, it appears that it looks like it's just water. However, it is still a mixture because there are salt molecules in there mixed in with your water molecules, right? So if we had a glass of water that's just H2O, and then we added salt to it, at first we're going to see the salt, and then maybe we stir, or over time we notice that the salt has completely dissolved. The salt is still in that water. If you were to taste the water, it would be salty. It's just that it is dissolved, so we can't see it, okay? The compounds do not glue to each other, okay? They're just a mixture. So there's just NaCl compounds and H2O compounds coexisting in the same glass. So it is a mixture, okay? Now it's a homogeneous mixture because it's uniformly mixed together. Anytime something dissolves, that creates a uniform mixture, meaning you can't really see the individual parts of the mixture because it's dissolved, okay, or it blended together. Like if you make a smoothie, before you blend the smoothie, it's a bunch of chunks of fruit, whatever else you put in your smoothies, okay? And then after you blend it, it has a nice uniform mixture, okay, or blended constant composition. You can't see anymore what individual pieces of fruit you have in that smoothie. You just know that it's a mixture of different types of fruits, okay? So the other thing I want to bring up is this little AQ that you see here. Now, in a few weeks, we're going to be learning about the phases of matter, okay? And we started talking about yesterday how when we see things written like this, okay, that's showing us a compound, okay? It's a chemical formula for salt, and it's showing us that a salt compound is one Na and one Cl chemically glued together. So that's a salt compound. It's called sodium chloride, okay? Now, sometimes we are going to be seeing these little letters in parentheses, okay? And what these stand for are the states of matter. So if you see a little S in parentheses, that's just solid salt. So that's solid table salt that you would find in your salt shaker, okay? An L would stand for liquid, and a G would stand for gas. So the little letters in parentheses, if they are placed next to a compound or next to a chemical formula, they tell us what state of matter it is in. Now, there are only 3 states of matter, solid, liquid, and gas, but there's also another little notation called AQ, okay? And what AQ means is that that substance is mixed with water, so dissolved or mixed in water, okay? So if you think AQ, right, again, if we use context clues, if we think aqua, that means water. So if you see NaCl, AQ, that means that the salt or the sodium chloride is mixed with aqua or water, okay? So it is dissolved in water, and that is a homogeneous mixture, okay? First of all, it's a mixture because it's 2 things mixed together and this physically mixed together in the same container, salt and water. And it's homogeneous because the salt dissolves and it creates a uniform substance. Now, some other examples of homogeneous mixtures, okay, Coca-Cola, okay? Coca-Cola, when you look at it, it just appears to be a liquid. You can't see all the different things that are added to Coca-Cola when you look at it, okay? But there's sugar in there, there's sweeteners, okay? There's carbon dioxide gas. But because it's a uniform mixture, it has a blended, constant composition, it's a homogeneous mixture, it is uniformly mixed throughout. We cannot see the individual ingredients in that soda bottle, okay? We just see what appears to be a liquid, okay? Same thing with lemonade. If you look at lemonade after all the powder has dissolved, you no longer see the powder, okay? That has dissolved, it has created a homogeneous mixture. Sugar in coffee, that is another homogeneous mixture. Again, if you have a cup of coffee, you can't tell if there's sugar in it until you taste it because that sugar has dissolved. But it's still a mixture of sugar and coffee, okay? Same thing with a smoothie. With a smoothie, let's say we put blueberries, raspberries, and bananas, okay? That's a mixture because it's 2 or more different things mixed together, physically mixed together. But when we blend it, that's when it becomes a homogeneous mixture because now there are no chunks in there, okay? It's blended and smooth and uniformly mixed together. Now, the opposite of a homogeneous mixture is something called a heterogeneous mixture. Now, a heterogeneous mixture, first of all, if we use our prefix, hetero meaning not the same or different, okay, it is 2 or more substances that do not blend smoothly throughout. So it's still a mixture. So both homogeneous and heterogeneous mixtures follow the same characteristics of a mixture. There are 2 or more substances that are physically combined, and they both can be physically separated. Okay. Now, with a heterogeneous mixture, it does not blend smoothly throughout. No, there's no dissolving. Nothing is blended together. The individual substances remain intact. So you could see all the individual pieces of that mixture still because each individual part of the mixture remains intact. And because it is a mixture, it's broken down by physical means. It can be broken down by physical means. Okay. Now, some examples would be like a fruit salad. A fruit salad is a heterogeneous mixture because it's 2 or more different things mixed together in the same container, physically combined, and each individual piece remains intact, right? So you could separate the strawberries from the blueberries from the bananas, whereas in the homogeneous mixture, if you blended that together, you now cannot separate the strawberries from the blueberries from the bananas, okay? Another heterogeneous mixture would be something like soil, okay? Sometimes if you pick up maybe a sample of soil, there's rocks in there might be fertilizer, there's dirt, there might be some worms, okay? It's a mixture of 2 or more different things where all the individual substances remain intact. Some other examples of a heterogeneous mixture, we said fruit salad, any kind of soup, right? That's a mixture of liquids and solids. Chex Mix, trail mix, those are all heterogeneous mixtures. Okay. Now, in terms of separating them, when we say they can be physically separated, since both are mixtures, both can be physically separated. Now, a heterogeneous mixture is a little bit easier to separate because you could simply, right, if you wanted to separate that fruit salad, you could pick apart all the fruit and separate all the fruits, right? Same thing kind of with the soup or with the Chex Mix. Another example of a heterogeneous mixture would be like if we had a glass of water and we added sand to it. Now, sand is not like salt or sugar. It does not dissolve in water, so it would just kind of fall to the bottom. So if you had this mixture of sand and water, you might want to do something like run it through a filter, okay? That might look like this, right? So let's say you have this mixture of insoluble solid, meaning the sand that does not dissolve in water, and you would set up this little filter paper with the water. The water would drip through, but because the sand particles are too big, it does not go through the filter paper. So that's one way you could separate that, okay? Now, if with homogeneous mixtures, because the individual pieces do not remain intact, because they either dissolve or they're blended, something like salt water, okay? Salt water, you cannot now filter out the salt because it's dissolved in the water. So if you pour salt water through a filter, nothing will remain on top of the filter, and all of the salt and all the water will come through because the salt has dissolved in the water. So for that, what you could do is boil the salt water. If you boil salt water, the water will evaporate and turn into a gas, okay? But salt does not evaporate. So the salt molecules will be left over, and you will be left with like a white crystal, which is your salt, okay? But both of those, boiling or filtering something out, both of those are physical means of separation. They don't require a chemical reaction. Boiling is not a chemical reaction. Okay, so we're just going to do two examples to practice. Number one goes along kind of with what we learned yesterday to wrap up this lesson, and number two is a little bit of what we learned today. So number one gives us these particle diagrams. It says which diagram represents a mixture. Okay, so the little black circles represent particle X, the little white circles represent particle Z. First of all, if we're looking for a mixture, we know it has to be two or more different substances. So we could automatically omit C and D because we only see one type of particle in those diagrams. Okay, then we have to remember that mixtures are physically combined. They are not chemically combined. They're not glued together by bonds. That would omit A, so we would be left with B, where particles X and Z are mixed together in the same container. Number two, which of the following represents a mixture? So with a question like this, you might not even know these fancy compounds. You don't need to know what NaCl is. You don't need to know what NH3 is, but we see those little letters in parentheses. And we remember that S stands for solid, L stands for liquid, G stands for gas, and AQ means it is mixed with water, right? You should think aqua, AQ, okay? Therefore, our answer would be A, because NaCl, AQ, means that NaCl compound is mixed, we're looking for a mixture, with water. Okay, the others, NaCl solid, right? That's just solid table salt. That's not a mixture. That's just table salt. That's just a compound. Same thing with NH3 liquid. That's just the compound NH3 in the liquid form. All right, so just to review, okay, today we defined the two types of mixtures, and we also went through examples of each. Okay, so we completed this lesson, and we will now complete our classwork.